All right. So, chapter 10 is talking about energy and work. And section 1 is the basic energy model. And before we get into that, let's talk about this. The car pulls away from a stop sign with constant acceleration. After traveling 10 meters, its speed is 5 meters per second. What will its speed be after traveling 40 meters?
B. I agree.
You think it's B?
Yep.
I don't.
Oh no. It's totally B.
No.
3 against 1. So, okay. You got 5 over 10. And then X over 40. So just that's what I did. And you get 20.
Wait, it might actually.
1/2.
Here, hold up. It took 10 meters to get to 5 meters per second.
Yeah.
No, I'm not looking up anything.
Another thing I can think of.
What's the important information in this problem?
Constant acceleration.
Constant acceleration. And what else?
It was at a stop.
It was at a stop because it was at a stop sign. So that means the initial velocity is 0. Okay. So now from kinematics, way back in the beginning of the year, here we're at the end of the year. Kinematics equation that would deal with constant acceleration and initial velocity. We want final velocity. So we have a VF, a VI, and an A.
I'm going to use my delta theta
VF equals VI plus acceleration times delta. We don't have delta T. VF squared equals VI initial squared plus 2 times acceleration times delta X.
Great. VF squared equals VI squared plus 2A delta X, right? Delta X?
Yeah.
Delta X. Okay. And that's perfect because we're talking about traveling 40 meters here. So delta X is exactly what we wanted. Now, what do we know?
We know velocity initial is 0.
That's right. This guy is out of there. Okay.
Acceleration, we don't know.
We don't know acceleration, but we know that it's constant, right?
Yeah.
Okay. What
We
will
know
its
final.
speed be? VF is what we're looking for.
Yeah.
So we're going to probably square root and find out VF, right?
Yeah.
So VF equals square root 2A delta X. So what do we notice now in this equation?
We have 2 variables.
Okay, but we first went 10 meters, and then we had gone 40 meters. So what happened to delta X?
It increased.
It increased by how much?
30.
Okay, but really it increased by a factor of 4. 10 meters to 40 meters, we went 4 times as far, right?
Mm-hmm.
So this right here got multiplied by 4.
So we have to multiply the other side by 4 too.
No, we don't multiply the other side by 4
So did you
because
just
that factor of 4 is going to be square rooted.
So 2 times 4 is
So
8.
2.
Square root 8A.
You're thinking too far. This right here is a constant. In both formulas, that 2A is going to be 2A, right? But that factor of 4 on the delta X gets square rooted and becomes 2.
So
4A.
4A delta X.
So if our speed was 5 meters per second, that factor of 4 on the delta X got square rooted and became 2 for the VF. That means that the velocity doubles. So the answer is 10 meters per second.
That dude is slow, in my
That's what I'm
opinion.
saying.
T.
So the name of this chapter is energy and work. We don't know what work is yet, but energy is a word that we hear all the time. So energy bars, energy drinks, chemical energy heats our homes, heats our bodies. Electrical energy runs our lights, runs our phones, runs our computers. Solar energy grows crops. and forests, and also can light our stuff. Don't waste your energy on that, right? So we use the word energy all the time. So in this chapter, we're going to be talking about different forms of energy: kinetic energy, potential energy, thermal energy. We kind of touch on chemical energy a little bit, but it's not really a focus of what we're doing. So our goal is to understand the characteristics of energy, how they're used, and especially how they're transformed from one form to another. So as we get going, we're going to be using different symbols, different notation, and then working on how to transform energy from one state to another, one form to another.
So like from kinetic to thermal?
From kinetic to potential and back and thermal and so on. Yep.
I know you can change kinetic to thermal.
Yeah. So here we go. Maybe slightly important law that we're going to talk about right now is the law of conservation of energy. Just in case you couldn't see it, it's here. The energy is neither created nor destroyed. If one form of energy in a system decreases, it must appear in an equal amount in another form. That is the law of conservation of energy, and you must know it.
I got a good feeling that on the test you're going to have us say it in our own words.
You think so?
I think so.
Maybe. I don't know. Many scientists consider this law of conservation of energy to be the most important of all the laws of nature. That might be why it is in giant font, bold, and huge.
Many scientists are nerds, so.
I don't know what to do with that statement.
Pretend you didn't hear it.
So, you cannot create nor destroy energy. If you decrease the energy in one form in your system, it has to be increased in an equal amount in some other form in your system. Pretty important information. All right, so we have systems and forms of energy. So in the little picture, we have a system and its energies. So we have inside the circle, the system can have many different kinds of energy. So in the circle, we have the system boundary. So we have these symbols, K, and then U sub G, U sub S, and then E sub TH, E sub chem, CHEM, and then E, capital E equals K plus U sub G plus U sub S plus E sub TH plus E sub chem plus blah, blah, blah. Okay? So the total energy is E, that capital E right there. And that is the sum of all of the energies that are present in the system. Now the question is, what are all these other things? The K and the U sub G and the U sub S. We don't know what those are just yet. So whether the system is simple or complex, it has a total energy capital E, which is the sum of all the different kinds of energies that are present in the system. The system can have many kinds of energy at one time. For example, a moving car has kinetic energy of motion, of course, because it's moving. As you'll find out, kinetic energy is the energy of motion. Chemical energy stored in gasoline. Thermal energy in its hot engine, and so on.
So is there such thing as mechanical? Like,
Mechanical energy?
yeah. Or is that just considered kinetic?
Kinetic energy, if you're moving. Mechanical energy, is it moving?
Yeah.
The following are examples of common types of energy. So here we go. Now, all these symbols here are different types of energy, so let's talk about some of those. Kinetic energy is K. So the energy of motion. All moving objects have kinetic energy. The heavier an object and the faster it moves, the more kinetic energy it has. So if it has more mass and it's moving, then it has more kinetic energy. If it's moving faster, then it has more kinetic energy. If you put those two things together, it has more kinetic energy, okay? The wrecking ball, this is a picture of a wrecking ball. So the ball is here, and then it's being suspended from this cable right here. Kind of hard to see in the picture. The heavier the object is, the faster it moves. So the wrecking ball is very, very heavy. And then if we get that thing swinging, it has a lot of momentum being slammed into that building. So it's effective in part because of that large kinetic energy. So it brings down the building very effectively. Gravitational potential energy. So that is U sub G.
How come it's U? Is there any particular reason?
Just a symbol. Gravitational potential energy is stored energy associated with an object's height above the ground. So the roller coaster has gravitational potential energy because it is above the ground a certain distance. So as the roller coaster ascends, energy is stored as gravitational potential energy. And then that potential energy is converted to kinetic energy as it begins to fall down the hill, okay, as we'll talk about. So the stored energy is converted into kinetic energy there. So we have U sub G as it climbs up the hill, and then once it gets to the top, it has a maximum potential energy, and then it starts to fall down the hill, and that potential energy is converted to kinetic energy, K.
So then anything that's not suspended would have gravitational potential energy. Like that wrecking ball doesn't because it's suspended by a cable. But
okay, so two different things. The wrecking ball swinging has kinetic energy. Because the ball itself is suspended, it would have gravitational potential energy. If the cable snapped, the ball would fall.
Okay. So
but that's two different things.
Anything that's pretty much not touching the ground
has potential energy.
Has gravitational potential energy.
Yes. Okay. So now elastic or spring potential energy. So that's U sub S. So spring is the S part. Elastic potential energy is stored when a spring or some sort of elastic object, like a rubber band, this archer's bow, we draw that string back, and now we have given it potential energy in the form of a spring, is stretched. The energy can later be transformed into the kinetic energy of the arrow. So we let go of that spring on the bow, or we let go of the rubber band, or whatever, and now that is converted into some sort of kinetic energy. In this case, in the picture, the arrow would be flying through the air. So we transfer that energy over to the arrow flying through the air. Okay? Thermal energy. So that is E sub TH. And you might recognize this picture here. This is one of the thermal pools in Yellowstone. Hot objects have more thermal energy than cold ones because the molecules in the hot object are jiggling around because they have all this heat associated with them. The thermal energy is the sum of microscopic kinetic and potential energies of all the molecules in the object. So this statement right here, kinetic and potential energies, it's the sum of those things for the energy that's stored thermally. So now we have K for kinetic energy. We have U sub G for gravitational potential. We have U sub S for spring potential. And we have E sub TH for thermal energy. Okay, moving on. So we have chemical energy now, the electric forces that cause atoms to bind together to make molecules. So we have energy can be stored in these bonds. Energy can be later released as the bonds are rearranged during chemical reactions. All animals eat, taking in chemical energy to provide energy to move muscles and fuel processes of the body. There's other things that we can talk about with chemical energy. Like I said, we're not going to focus too much on chemical energy. We talk about it a little bit here and there, but E sub chem is our chemical energy symbol. And then we also have nuclear energy. This picture right here is showing the beginning stages of a nuclear detonation. The forces that hold together the particles in the nucleus of an atom are much stronger than the electric forces that hold together molecules. So they store a great deal more energy. So if we were to break apart the nucleus of an atom, splitting an atom, we're going to release a ton of energy.
It's so crazy to think of that tiny little thing.
I know, it's amazing. E sub nuclear is our symbol for nuclear energy.
We won't be using that a whole lot, will we?
No.
I hope we do a project.
This is not another one that we focus on here.
I would love, I would hate to write out E sub nuclear.
I know, yeah, it would be a lot. I'm with you. But certain nuclei break apart into smaller fragments, releasing nuclear energy. The energy is transformed into kinetic energy of the fragments and then into thermal energy, form of heat. So, yeah, it's pretty amazing stuff that we could talk about there. A nuclear fusion and nuclear fission. We're talking about nuclear fission here. okay, breaking the atom apart. So there you go. Now we have energy transformations. So like I said here, what makes the world interesting is that one kind of energy can be transformed into another. So we can transform potential into kinetic. And that's really the thing that we focus the most on, or kinetic into potential. If that couldn't happen, it would be a pretty boring world if you think about it. Because then we just have, you know,
Static.
everything would just be kind of sitting still all the time.
Like the heat death of the universe.
I'd have my wrecking ball sitting there. I cut the cable and the wrecking ball just continues to sit there, right? Like we would never move. Nothing would ever happen.
Oh,
Temperatures would never
Cyrus's
change.
wrecking ball would never come to pass.
So for energy transformations, we use a shorthand notation. This symbol right here, the arrow, will tell us how we're transforming our energy. And so how this would work is if I had potential energy, let's say gravitational potential energy, U sub G, I transform it into kinetic energy, I'd have K. Okay, so that's how that's going to end up looking, just as an example.
Ugh.
Did you say ugh on purpose?
All right, so here are some examples of energy transformations. Weightlifter lifts a barbell over her head. So the barbell has much more gravitational potential energy when high above her head than when on the floor. So because we lifted it up, we gave it potential energy. So to lift the barbell, she transforms chemical energy in her body. She's burning,
Calories.
okay, good, and transforming that energy in her body into gravitational potential energy of the barbell. So the chemical process that happened here, or the process that happened here, was E sub chem turned into U sub G. Okay? The base runner slides into the base. So for this to happen, when running, he has lots of kinetic energy, of course. After sliding, he has none because he came to a stop. So no more kinetic energy. So that energy must have been transferred into something. His kinetic energy is transformed mainly into thermal energy. Why?
Because friction.
Because of the friction of him sliding in the dirt. And that's so now his leg is heated up some. So the ground on his legs are slightly warmer. So the kinetic energy here transforms into energy thermal. Okay?
Like that?
Burning a campfire. So the wood here contains considerable chemical energy. When we light it on fire, the carbon in the wood combines chemically with the oxygen in the air, and the chemical energy is transformed largely into thermal energy, the hot gases and embers, and we warm up. So energy chemical in the wood transforms into energy thermal that we feel. And then it escapes into the atmosphere.
You don't ever think about like fire being a chemical reaction all that much.
Oh, I do now after taking chemistry in this class. It's like,
Yeah.
oh look, chemical reaction.
All right, so this is a two-step process here for the springboard diver. The energy transformation that's going on here is when we look at the picture right now, we have the board being flexed. So the elastic potential energy that's stored in the board as the board, so we have a second board sitting right here. The board in its relaxed state is acting like a spring right now. So we have potential energy as a spring. Now it's flexed. So soon the energy will, it says, begin to be transformed into kinetic energy. So as the diver begins to leave the board, now the spring potential energy is going to be transformed into kinetic energy given to the diver. And then as the diver rises into the air, so now the diver is like being launched up, right? When the diver reaches this maximum height up here, all of the diver's kinetic energy has been transformed into potential energy because the diver is slowing down and coming to like an instantaneous stop.
But then it goes back into kinetic.
But then the diver will turn back into kinetic energy as he begins to fall again, right?
Or gravitation.
The gravitational energy is maximum up here, no kinetic as he comes to a stop. But then he will continue, and this would turn back into kinetic.
It could also go in the other way too, because when he runs up to the board, that's chemical, and then when he jumps, that's more gravitation.
Yeah, we could take this to all kinds of limits, right? So that's the idea that's going on here. If we just look at what's presented in the picture. The spring potential on the board turns into kinetic given to the diver, and then the diver will start to go up, and that will turn into potential gravitational. Okay? Making sense?
Mhm.
So that's how these diagrams will work, these little energy transformation diagrams. So as you see them, kind of that's how you're going to have to proceed. So energy transformations within a system. So the system is the big circle kind of enveloping the entire, kind of containing this little sub diagram. Energy transformations that are going on within the system. So we have kinetic sitting here, we have potential sitting here, and then chemical energy sitting here. Now, notice it says energy transformations are changes of energy within the system from one form to another. So the arrows are going both ways. I can turn kinetic into potential and potential into kinetic. I can turn kinetic into chemical and chemical into kinetic, and likewise potential into chemical and chemical into potential. But notice that once I turn chemical into thermal, thermal does not go the other way. Okay? So once I start losing energy to thermal, I cannot get it back. So like the guy sliding into second base, that thermal energy that he lost his kinetic energy to, the heat that he gained on his leg from sliding into second base, that thermal energy is going to be lost. He can't get it back.
So, okay, but now how does that follow the
It's still in the system, but it's not, he can't turn it back into kinetic.
So what does that end? Can that the energy just stays thermal?
Yeah, it can't go anywhere else but thermal.
The heat death of the universe.
Oh.
Okay? So once it becomes thermal, it does not go back. All right? So energy, remember, this is your equation here. Energy is kinetic plus potential plus thermal plus chemical and so on. So the thermal is still in the system, but it cannot be transformed back into something else. It's done. Okay? So the directions of the arrows in this figure, it's easy to transform energy from kinetic to potential, but it's not possible to transform thermal to kinetic in the diver or the baseball player sliding example. Okay?
We're not really using our work. Right?
All right, so energy transfers and work. So energy transformations occur between forms of energy within the system. So transformations are within a system. Every physical system also interacts with the world around it. So in other words, within the environment. So an exchange of energy between the system and the environment is called an energy transfer. So between the system and the environment is an energy transfer. So if we are doing energy transformations within the system, that's fine. But if we're talking about exchanging energy between the system and the external environment outside of the system, then that is an energy transfer. So we need to keep those two words straight, transformations and transfers. So there are two primary energy transfer processes. These two right here, work and heat. So work is mechanical transfer of energy from the environment to the system or vice versa by pushing or pulling on it. So that's a mechanical thing that is being done. And heat is non-mechanical transfer of energy to the system or vice versa because of a temperature difference between the two. So one is mechanical, the other one is because of temperature differences. Heat, that's kind of obvious. Work is because of something mechanical that was done. Okay? So the name of this section, remember, is energy and work. So now we're finally getting into the work side of things. All right, so we have work and heat, our energy transfers into the system. So we have our system diagram again over here in the little circle. Now we're going to transfer energy from the environment to the system or from the system to the environment, and that's work and heat. So that's these guys over here. We're putting energy in or we're taking energy out, one way or the other. That's how that's done. The basic energy model for the isolated system, modified to include energy transfer in and out of the system, as well as energy transformations within the system. So that's the complete diagram now. In this chapter, we're considering energy transfers by means of work. Okay, so the heat aspect here is not something that we're really going to be talking about. It's going to be work. So in physics, work is the process of transferring energy from the environment to the system or from the system to the environment, done by applying mechanical forces, which is pushes and pulls to the system. So the form that the energy takes depends on the details of the system and how the forces are applied. And the symbol for work is capital W.
So with
Okay, so we have this guy's throwing a shot put. We have the shot being the system. The environment then is the athlete. And as the athlete pushes on the shot to get it moving, he's doing work on the system. So he is pushing the shot. He's doing work on it then. He's transferring energy from himself to the shot. The energy transferred to the system appears as kinetic energy. The transfer is W, work, becomes kinetic energy. Striking a match. The system is the match in the matchbox. The environment is the hand. That is what is doing the work. The hand quickly pulls the match across the box. The hand does the work on the system, increasing its thermal energy. The match head becomes hot enough to ignite. Work. And then we have this guy. That's your thermal energy. Okay? So work transfers over to thermal energy. Firing a slingshot, the system is the slingshot. The environment is the boy. He's the one doing the work. The boy pulls back on the elastic band. He does work on the system, increasing the elastic potential energy. So notice what the environment is. It's the thing doing the work. Okay? So the transfer then, in this case, the work is transferring over to the potential energy stored as a spring. So in each example, the environment is applying a force. So the environment is the thing that is doing the work, the thing that applies the force. While the system is undergoing the displacement, the system is the thing that's being moved. Energy is transferred as work only when the system moves while the force acts. The force applied to a stationary object pushing against a wall transfers no energy to the object and therefore does no work. So it has to move. Notice that also that the energy is being transferred from the athlete to the shot by the force of his hand. We say he does work on the shot. The other examples are similar. The hand does work on the match. The boy does work on the slingshot. Okay, so the environment has to apply a force to cause something to move. Otherwise, no work is done. Okay? All right, so the law of conservation of energy. The concept of the law is here. Work done on a system represents the energy that is transferred into or out of the system. The transferred energy changes the system's energy by exactly the amount of work that was done. If the change in energy is delta E, then we can write delta E equals work. So we know that the total energy E is the sum of all of the different energies in the system. We've seen that already. Therefore, the change in E is the sum of all the changes in the different energies present. So now we have what's known as the work energy equation. You're going to be using this to solve problems. The work energy equation is delta E equals delta K plus delta potential gravitational plus delta thermal energy plus delta chemical energy plus whatever else energies there is equals work. This equation is a mathematical representation of the basic energy model presented earlier. That model and this equation are the heart of what the subject of energy is all about. And you're going to be using it all the time.
Takes a lot of energy to do some work, doesn't it?
All right, suppose we have an isolated system such that no energy is transferred into or out of the system. That means no work is being done on the system. Isolated system, nothing being transferred in or out. Work is how we transfer in or out, so no work is being done.
So no movement?
Didn't say that. No, the energy inside the system may be transformed from one form to another, but the total energy remains constant. This means the total energy for the system is conserved. So for an isolated system, work equals zero. It's an isolated system. We're not transferring energy in or out. Work equals zero. The law of conservation of energy, the total energy for an isolated system remains constant. So here is our work energy equation once more, but now it equals zero because there's no work being done. This law is similar to the conservation of momentum. A system's momentum changes when an external force acts on it, but the total momentum of an isolated system does not change because no external force is acting on it. Here we have no external energy, so we will have no work, so equals zero is what we get. We will solve energy problems in a similar before and after way as we were doing with momentum. Okay?
Sounds good.
A roller coaster slows as it goes up a hill. So therefore, the energy transformation is which one?
I think it's
Yeah. It's slowing as it goes up the hill, so kinetic energy is being transferred or transformed?
Transfer.
Transformed. Kinetic energy is being transformed into gravitational potential energy. So K is being transformed into U sub G. That's C. And that's it. That's the whole section.
Hooray.